Hello, welcome to the third lecture of logic, and today we will talk how to solve propositional formulas. We have introduced the language of propositional logic in the last two lectures. We talked about syntax, we introduced formulas of a special structure, the formulas in conjunctive normal form. We talked about the semantics of the formulas, we talked about properties of the formulas, and we have also seen some very simple encodings indicating how propositional formulas are used. Today we will talk about how to decide the satisfiability of propositional formulas and respectively other properties like validity or unsatisfiability, which go together. And what we want to do today is not using these rather naive approaches that we have seen before, where we enumerate all possible assignments in order to see if a formula has a satisfying assignment or not. But what we will do today is we will introduce two calculi which analyze or which provide rules that can be applied according to the structure of the formulas, of the formula under consideration, and then use structural information to decide satisfiability or validity of a formula. And before we do so, let's talk a bit about logical reasoning and logical entailment. So why we are interested, or what is one of the benefits and strengths of a logical formalism, and this does not apply only to propositional logic but to other logic as well, is that logics provide some reasoning mechanism. What does this mean? If we know that certain formulas hold, we can ask the question if another one holds as well. And this kind of reasoning is called entailment. Here I have it formalized. So we are given n formulas, phi 1 to phi n, plus an additional formula psi. In our case, these are propositional formulas. And then we say phi 1 to phi n entail the formula psi if and only if psi 1, if and only if we have that if phi 1 is true, phi 2 is true, phi n is true, so all of the phi I formulas are true. If this is the case, then it follows that psi is also true. Yeah? So when we have a satisfying assignment for phi 1 to phi n, then this satisfying assignment is also a satisfying assignment of psi. Yeah? Then we say that phi 1 to phi n entail the formula psi. And for this entailment relationship, we also have a meter symbol, as we had it, for example, for equivalence. And we write it here with this entailment symbol. And on the left-hand side, we have phi 1 to phi n. And on the right-hand side, we have the psi. Yeah? And this entailment relationship is true if this property stated here holds. Yeah? And we can also express this entailment property in terms of a propositional formula. Here we use implication, and we do this in such a case that phi 1 to phi n entails psi if and only if the formula phi 1 and phi 2 and so on and phi n implies psi is a valid formula. Yeah? So no matter which assignment I chose, this implication here evaluates to true. And this is again a trick where we express a semantic property in terms of a syntactical representation or characterization. And yeah, if these n formulas do not entail psi, then we just cross this entailment symbol out. Yeah? And here I have some examples. In the first case, we say A entails A or B. Yeah, this is obviously the case, because if A is true, then also A or B is true. Here in the second case, we state that A, B entails A and B. Yeah? Whenever A and B are both true, then also their conjunction is true. Very simple example. However, if we would have just here A alone would not entail A and B. Yeah, this would not be enough. Yeah, here in the middle we have a very interesting case. On the left hand side we have no formula given. Yeah, so here nothing is written down, and this means that we have the empty conjunction. Yeah, because this n phi's can be read as a conjunction, and if we have the empty conjunction, then we have top here. Yeah, and what we say, top entails a formula, in this case A or B, and what it says is that the formula on the right hand side is a valid formula, because no matter how I assign the values for any variables occurring in the right hand side formula, they evaluate, the right hand side formula evaluates to true if the left hand side formula evaluates to true. But if the left hand side formula is top, then we require that the right hand side formula is a tautology. Yeah? And here it is the case. However, it's not the case for A and not A. Yeah? So this entailment does not hold. Top does not entail A and not A. Here in the third column on the top we have something interesting. We have A as the first formula, and we have A implies B, and the claim is that this entails B. This we can also check. Whenever A is true, then it depends on the value of B if all formulas on the left hand side are true. If A is true and B is false, then we have true implies false, and this here is false, and therefore we have false on the left hand side, and therefore we do not have to check what is on the right hand side. But if A is true and B is true, then this A implies B is true, because true implies true is true, and since B is true, this entailment holds. And what we have here is this is a rule called modus ponens. So we know that, so we have a rule that B follows from A, and we know A, and then we can conclude B. Yeah, here in this case, this is now very simple, but this is in fact an extremely powerful inference rule which enables logical reasoning. Okay, and here as a last example, on the left hand side we have bottom entails anything. Yeah, so if we have bottom on the left hand side, there is, no matter which assignment I choose, it can never make this left hand side true, so it doesn't matter what we have on the right hand side, this entailment always holds. So from false, from bottom, everything follows. Yeah? Good. So this is about the entailment relationship, and this allows us now to give a notion of formula strength, so to relate to formulas. We say a formula phi is stronger than a formula psi if and only if phi entails psi. So whenever phi is true, then also psi is true. A formula psi, on the other hand, is weaker than a formula phi if and only if phi entails psi. And they are equally strong if and only if phi entails psi and psi entails phi. Here we have some examples, and we will also prove this first one here. A XOR B is stronger than A or B. Yeah? So whenever A XOR B is true, and A XOR B is true if A and B are different, then also A or B is true, what is obviously the case. Yeah? Because A or B is true when A is true and B is false, or when A is false and B is true, and in both cases A or B is true. Yeah? Okay, then A and B is stronger than A or B. A and B is only true if A and B are both true, and in this case A or B is also true. And the strongest formula we have is bottom. Yeah, bottom never becomes true, therefore it's the strongest formula. And the weakest formula we have is top. This one is always true, and therefore every other formula, so there is no weaker formula than top. Okay, so this is about reasoning, and what we want to do now is we want to reason with the satisfiability problem. So let us quickly recall what is satisfiability checking, what is SAT. We're given a propositional formula phi, and we want to know if there is an assignment under which the formula phi evaluates to true. This problem is the oldest NP-complete problem, meaning that it has the following properties. Finding a solution is extremely difficult. Probably it's exponential in the worst case. Yeah? So if we have n variables in a formula, then in the worst case we have to check 2 to the power of n possibilities. But if we have a candidate solution, then it's very easy to verify if this is indeed a solution. We just plug in the values into the formula and then check the result and see if the formula is true. So this can be done in polynomial, with polynomial effort, by just going over the formula. So we have a problem that is non-deterministic polynomial. And because of this complexity, SAT, or the decision problem of propositional logic, is an interesting problem for encoding many other practical problems that occur in industry, that also occur in math, or in various AI applications. To encode these problems as propositional problem and check it with a SAT solver, because there are a lot of problems which are NP hard as well, and therefore the efficient tools that are available for SAT can be used to solve these problems, and then it's not necessary to develop a new dedicated solver. And with a SAT solver, other reasoning problems can be solved as well, so other reasoning problems, and this we already discussed in the previous lecture. We can check if a formula is valid by negating the formula and seeing if the negation of the formula is unsatisfiable. We can check if a formula phi is refutable by negating it and checking if not phi is satisfiable. Because if phi is refutable, it has a counter model, and this counter model is a model to not phi. Then if we want to check if two formulas are equivalent, so if we want to know if they have the same truth value under each assignment, then we can translate this to not phi is equivalent to psi and see if this formula is unsatisfiable. We have to check that phi is equivalent to psi is valid, And in order to check validity with a SAT solver, we check if the negation is unsatisfiable. This is what we do here. And finally, for the entailment, we can express the entailment in terms of an implication, as we have seen on the previous slide. So we translate it to phi 1 and phi 2 and so on, and phi n implies psi. And we check if this formula is valid. And for checking if it is valid, we have to negate it and check if the negation of it is unsatisfiable. And the negation of this implication representation is the formula we have here. Yeah? So we can rewrite implication as a disjunction. So phi implies psi is the same as not phi or psi, and if we negate it, we get this kind of formula. Okay, so this is why we can transform one of these reasoning problems into another, and therefore it's enough if we have a procedure to decide unsatisfiability or to decide satisfiability, or if we can do validity checking, we can also do satisfiability checking. And what we will now do is we will introduce two different calculi that allow us to automatically reason about a propositional formula. So what we want to do is we want to mechanically show validity in one case, and in the other case unsatisfiability. And with this, we can solve satisfiability as well. And the idea is to use simple syntactical manipulation to prove validity or refute a formula. And we do not talk about individual assignments, we just look at the structure of the formula and apply rules which fit according to the structure of the formula. And the elements of a calculus are as follows. On the one hand, we have axioms. So these are expressions that trivially hold or trivially lead to contradiction, or that are basically given. And then we have a rule we have a set of rules that allow us to derive new formulas in order to derive, for example, a contradiction or an axiom that trivially holds. And the approach is to apply the rules of a calculus until only axioms are inferred or until a contradiction is inferred. And if this somehow is not possible, then we conclude that the formula is valid or unsatisfiable. We will soon see what this means. And we will consider two examples of calculi. First, we will talk about resolution calculus, which works on conjunctive normal form formulas, and with this we can show unsatisfiability. And second, we will talk about sequence calculus, which allows us to prove that the formula is valid. Resolution. In resolution we have one inference rule, and this rule works as follows. We have two clauses, so resolution works on formulas in CNF. And we have two clauses. One clause contains a literal X, the other clause contains a literal not X, and we then infer a new clause C or D. Yeah? So if we have a clause X or C and another clause not X or D, where D are disjunctions of literals, we infer a clause C or D. Yeah, so C and D are possibly empty clauses, and we call this newly derived clause the resolvent, and the variable X is the pivot variable of the application of the resolution rule. And X or C and not X or D are called antecedents, and we assume that they are not tautological. And what we are also not interested in is deriving here a tautology, because what we want to do is we want to derive a contradiction, meaning that we want to apply the rules such that we can show that the formula under consideration, which is a CNF formula, is unsatisfiable by deriving the empty clause. Yeah? Let's look at the example here. So if we have two clauses, y and not y, so we have two unary clauses, then from this we can derive the empty clause. If we, this is a very simple example, yeah, and if we're at this stage, we can immediately see that the formula is unsatisfiable, because this means we have clause y, and conjunctively connected we have the clause not y, and this definitely leads to a contradiction. Okay, here we have a bit of a more complicated example. We have x or y or not z, and here we have not x, y prime or not z. And when we apply the resolution rule, then x is our pivot variable, and we get a new clause y or not z or y prime. I didn't write the not z again. Yeah. So we get this new clause here. Yeah. And what we're trying to do is we're trying to make the clauses smaller and smaller until we can derive the empty clause. What is not useful in order to derive a contradiction is the derivation of a tautology. If we have, for example, this situation, x or a is one clause and not x or not a is the other clause, then what is important here is that we do not have two pivots, but we have only one pivot. Yeah, and say x is our pivot, then we derive a clause a or not a, which is a tautology. Yeah, and this we cannot use in order to derive a contradiction, because this clause is always true. Yeah, and what would be completely wrong is if we would derive the empty clause already from this two by using two pivots, but this is unsound, what can be shown very easily. Maybe we'll discuss this in the exercise class. And what is important is that the resolution is sound, meaning that if we show that a formula is unsatisfiable, it is indeed unsatisfiable, and it's complete. For any unsatisfiable formula, we can derive the empty clause. Yeah? So if we derive the empty clause, the formula is indeed unsatisfiable, and for any unsatisfiable formula, we can derive the empty clause. Important is that in the worst case, we still have an exponential effort, so we can construct formulas where the resolution derivation is exponential. So we do not have a compact way of solving the formula in general, but often it works pretty well and we get short resolution proofs. Yeah, we call these derivations also resolution proofs. And so that's it. I would like to switch to writing space to give you some additional explanations. So let's think a bit, what does this resolution rule mean, and why does it make sense? So I will not prove soundness and completeness, but I will try to give you some intuition about this rule. Yeah, assume we have a clause x or c, and we have another clause not x or d. Yeah? This clause here we can also write as x implies d, and this clause here we can write as not x implies c. Okay, so here we have the situation that not x implies c, and here we have the situation x implies d. Yeah, but if we have this, we can also write this as follows: if x, then d D else C. Yeah? So if X is true, then we have to find an assignment that satisfies D. Otherwise, we have to find an assignment that satisfies C. Yeah? Because if X is true, then this first clause is definitely satisfied. If X is false, the second clause is satisfied. And in case the formula is satisfiable, yeah, we have to consider two cases, and this follows exactly from this. If X is true, let's find it like this: X is true. So if we have an assignment where X is true, then we can immediately then see that X or C is true, and we need some assignment for other variables. Not X or D is true if D is true under this assignment. Yeah? Under this assignment. Under assignment. We say X is true under assignment. Let's add this here. So X is true under assignment V. Then it follows automatically that X or C is true under V. And not X or D is true if and only if D is true under this assignment V. Yeah. So this is the one case, and the other case, X is false under an assignment V prime, then not X or D is true under V prime, and X or C is true if C is true under V prime. Yeah, and these are the two cases we have, yeah, because either X is set to true in an assignment or X is set to false under an assignment. And if we now have the clause D or C or D, doesn't matter, then this clause is true under V if D is true under V, and it's true under V prime if C is true under V prime. And since we have a disjunction, in both cases, if we find an assignment that satisfies the two clauses, we also have an assignment that satisfies this clause. Yeah? And therefore, it does not destroy the satisfiability of a formula if we add this clause. So if we have this conjunction X or C and not X or D, and D or C, then this has the same truth value under any assignment as the formula consisting only of the two clauses. Yeah? And the idea is now that we try to add constraints, that we try to add clauses until we get a contradiction. And I would like to show you now some small example. On the slides I have a big one. So let's consider this formula we already know very well. We have A or B and A or not B, and not A or B, and not A or not B. Okay, this is our formula, and we have all possible combinations of A and B, and we will not find an assignment that makes this formula true. And if we now do a resolution proof, we can start with taking clauses A or B and A or not B. Then B is the pivot, and we can derive the clause A. And if we take clauses A or B, not A or B, and not A or not B, then here we can derive the clause of size 1, not A. And if we now take this clause A and this clause not A, we can derive the empty clause bottom. Yeah. What I often see is that people do the following. They say, oh, okay, we have A or B here, and we have not A or not B, and they say A is a pivot and B is also a pivot at the same time, and then we immediately derive bottom. But this is not correct. Yeah? We may take only one pivot, and as I mentioned before, if we have A or B and not A or not B, and take for example B now as the pivot, then we would derive the clause A or not A, yeah, which is a tautology, and this one doesn't help us to derive a contradiction, so we will not do this. And we immediately see that this derivation here is incorrect, because if we have the formula A or B and not A or not B, then this is a formula which is satisfiable. For example, A not B is a model. Yeah, so it would be incorrect to derive a contradiction saying this formula is unsatisfiable, and this we could here do only because we applied the rule in a wrong way. Yeah? And in fact, if we have A or B and not A or not B, then we derive A or not A, or we could also derive B or not B, but we cannot derive the contradiction. This would be wrong. Okay, this is what I wanted to show you about resolution. On the slide you find a big example for a larger formula, and let's quickly look at this formula. Okay, so here we have given a formula that consists of 1, 2, 3, 4, 5, 6, 7 clauses, and now it's a bit more tricky to find a proof showing that this formula is unsatisfiable, and we also do not see this just by looking at the formula. Yeah. And what is also important to mention is that the proofs are not unique. You can do them in different ways. The important thing is that at some point a contradiction will be derived. Yeah? So here we could start, for example, with using the clause x3 or not x4, and the clause not x2, not x3, and with this we can use x3 as a pivot and derive not x2, not x4. Yeah, this we can derive with this clause, which comes from the formula. We can derive not x4. This not x4 we can use to derive x5. X5 we can use to derive not x1. So we already have a lot of clauses of size 1 that are useful. This not x4 we can also use to derive a clause of size 2, x1 or not x2. This unit clause x6 we can use to derive x1, and then we have not x1, x1, and we derive the empty clause. Yeah, we could also write bottom here. And this is how resolution works. Yeah, it might be tricky to find the proof, but if the formula is unsatisfiable, we will always find a proof showing unsatisfiability. If the formula is satisfiable, then we will not find an empty clause, and although there are a lot of possibilities to build resolvents, at some points we have done all possible applications of the resolution rule, and then we will not, when we conclude that no more application of the resolution rule is possible, then we know the formula is satisfiable. Yeah? This is a good thing about propositional logic, that we can also decide satisfiability by exhaustively building all possible resolvents and then concluding no contradiction can be derived, and therefore the formula is satisfiable. Okay, with this I conclude the discussion on resolution, and now let's have a look at the sequent calculus. So first of all, let us introduce the notion of a sequent. A sequent is an expression of the form phi 1 to phi n, where these are propositional formula. Then we have this sequence symbol, and on the other hand, on the right hand side, we have one single formula. Yeah, and all of these formulas are propositional formulas, and the formulas on the left hand side we call assumptions, and the formula on the right hand side we call goal. And like with the entailment, which looks very similar, like this symbol, a sequent intuitively means that goal psi follows from assumptions phi 1 to phi n. Yeah, and we have a special case where we do not have any assumption, and when we have this sequent where on the left hand side nothing is written, and on the right hand side we have the formula psi, then we want to prove that the formula psi is valid. Yeah? And for this we will introduce rules that allow us to prove that formula psi is valid. Before we do so, some words on notation. If we have a lot of formulas on the left hand side, we sometimes abbreviate it and write k ... and psi I is the formula that is relevant for the application of a rule. Yeah? So we do not repeat always the formulas, but sometimes abbreviate them with a k and indicate in which of the assumptions we are interested. And what is also important, we do not require an order on the assumptions, so it doesn't matter in which order we write down the formulas. Yeah? If you look this up in the literature, you will find a lot of variants where sometimes the order plays a role, where multiple formulas on the right hand side are allowed, and so on. And in principle these calculi work the same, but we have here a very simple version that we use, and but in principle the concept is very much the same. It just works in a bit different how rules are applied. Okay, so first of all we have axioms. Yeah, so we have various rules and we have axioms, and axioms are expressions which are always true, which hold by definition, and in our system we have two axioms. Yeah? One axiom has the following structure. On the left hand side we have a formula psi, and this formula psi is also the goal. So we do not care what other formulas are here on the left hand side, but the assumptions contain the goal. Therefore we call this rule goal in assumption. Yeah? And obviously a formula psi always follows from a formula psi. Yeah? And here we have maybe additional constraints by other formulas, but whenever this is true, also this has to be true, because this psi has to be true, and then this psi on the right hand side is, when this psi on the right hand side, on the left hand side is true, then also the psi on the right hand side is true. Yeah? And the second axiom we have is contradiction in assumption. And if we have contradicting assumption, then anything can be proven. Yeah. So if here on the left hand side we have phi and not phi, then it doesn't matter what we have on the right hand side. This the assumptions are always false, because either phi is true and not psi is false, or vice versa. Therefore, the assumptions never can be true, and therefore it doesn't matter what we have on the other side. So this is the other axiom we have, and we call this axiom contradiction in assumptions. Okay, so these are the axioms, and now we introduce rules for the different connectives that we have. And what we have to do is we have to define rules based on the side, based on which side of the sequence symbol a formula is located. So we have always rules for the left hand side and for the right hand side, and for every symbol that or every connective that we use, we introduce a rule. And we in sequent calculus, a rule consists of something like this we have here, and we have here on the top one or multiple premises saying this holds, and if this premise hold, then we can infer that a conclusion holds. Yeah. Let's, for example, consider this formula here, where we have as premise that we have some assumptions, and these assumptions entail bottom. Yeah, if this holds, then and on the left hand side we have a formula phi, and if this holds, we can conclude that it also holds that the assumptions here entail the formula not phi. Yeah? So we can also read this in the other direction. We want to show that not phi is valid, so we want to prove not phi. Therefore, we assume that phi holds, and we prove that this leads to a contradiction. Yeah? And when we want to prove a formula, then we use these rules not in a top-down manner, but we use it in a bottom-up manner. So we have this rule here. So we want to prove this formula not phi. And if we want to prove formula not phi, we assume that phi holds and show that this leads to a contradiction. And if we can show that we can apply all the rules we have until we get only axioms, then we know that the formula is indeed valid. Yeah, this is the basic idea. And now we have to introduce the rules that we have for each connective and each side of the sequent rule. Here I have the negation on the left hand side. So if I have a not phi in the assumption and psi is the goal, then this says we know that not phi holds and we have to prove psi. Then we could also assume not psi and prove phi. Yeah, so we move the psi to the other side by negating it, and the same we do for the phi, and have it here now on the right hand side. Yeah, and if we are the connective we are considering has to be the topmost symbol of some of the, either of some of the assumption. If it's in one assumption, then we have here this A. If it's in the goal formula, the topmost symbol, then we call the rule with a P and the connective. Yeah? And in the literature you also will find left and right for the rule names. Yeah, then here we have a very simple negation, a simple rule. This rule is the elimination of double negation. If we have a formula not psi on the right hand side, then the rule P not D, so this is the elimination of double negation, is simply having then psi as the goal on the left hand side. So if we want to prove that not psi is valid, then it's enough to show that psi is valid under some assumption. Yeah? And read in the other direction, if we know that psi follows from some assumptions, then we can conclude that not psi also follows from this assumption. And similar for the case that we have the double negation in a formula on the left hand side in an assumption, then we can, if we want to show that psi follows from some assumption, including one assumption that contains double negation on topmost connective, then we can also show that psi follows from assumption where psi stands directly there and the double negation is removed. Yeah, then we have rules for conjunction and disjunction. If we have in the assumption a conjunction phi1 and phi2, from which we want to show that psi holds, we can simply eliminate the conjunction and put a comma there saying that phi1 has to hold and psi2 has to hold. Yeah? So both of them, if both of them, so these conjunctions are true only if both of them are true, and this we can also express here by just considering phi1 and phi2 independent of the conjunction. Just write down the two formulas here on the left. It's a bit more tricky if we have a conjunction as a topmost symbol on the right hand side. So what does this mean? If the formula, if we want to prove the formula psi1 and psi2 and want to show that this follows from some assumption, we have to show that psi1 follows from the assumption and we have to show that psi2 follows from the assumption. So we have now two cases we have to consider. Yeah? So we have to show that psi1 is a valid formula and we have to show that psi2 is also a valid formula in case we do not have any assumptions. Yeah? In case the assumption set is empty. Okay, then now for the disjunction. Let's start with having the disjunction in the assumptions. Here we have now the case split, because if this disjunction phi1 or phi2 is true, then this can be because phi1 is true, or it can be because phi2 is true. And so we have to make this case distinction, because whenever the assumptions are true, then also psi should be true, and we consider the case that phi1 is true, and we consider the case that phi2 is true. Yeah? So we have this case split here. Okay, and if we have a disjunction on the right hand side, then it's enough that one of the two formulas evaluates to true if the assumptions evaluate to true, and therefore we say, and the other formula can be false. So we have two choices. Either we show the validity of phi 2 and say of psi 2 and say that psi 1, we assume that psi 1 does not hold. And the more formulas are here on the left hand side, the more likely it becomes false. So this helps just as an intuition. And this is the one case. And for the other case, we show that psi 1 is valid and assume that psi 2 and assume the negation of psi 2. Yeah, and we could, so, and the important thing is that these two rules are interdeterministic. Either we can do this one or we can do the second one. For implication, equivalence, and other connectives, we can introduce similar rules. Okay, this looks a bit complicated. Here I have a summary of some terminology. We have premises, we have conclusion. Premises are above a rule, conclusions below a rule. An axiom is a rule without premises, it just holds. We have one non-deterministic rule. We have here two choices how we handle this disjunction on the right hand side. A further non-determinism in the search is that we have multiple choices which rule to apply next, because we can have multiple antecedents, and then we have to decide which rule we use for continuing. And we have also rules with a case split, conjunction on the right hand side and disjunction on the left hand side. And if we want to show that the formula is psi is valid, we start with a sequence where the left hand side is empty and psi is the goal on the right hand side, and we apply rules from bottom to top as long as possible. So for a given conclusion we find a suitable premise or multiple premises, and if we are able to show that all branches can be closed by axioms, we know that the formula is valid. Because we could also read the proof in the other direction. We start from the axioms and then apply those axioms to derive the formula we are considering, but this is much more complicated. It's better to start with the formula and then apply the rules and obtain the axioms. But we will see soon in an example. And if all sequences are axioms, we can conclude that the formula is valid. And yeah, as I mentioned before, there are many different variants in the literature, so don't get confused if you look at a book and if the sequent calculus looks a bit different. Yeah, here I have written down the whole procedure or the application of the rule as code. I don't want to discuss this in detail, but if you do not like the reading of the rules we have before, you can go over the code and see what is happening. So how the set of assumptions is increased and how the formula of the goal formula is changed by the application of the rules. Yeah. So, but this is here just the same what we discussed before, but written down as code. Okay, but now let's have a look at an example. We want to show that XOR is stronger than OR. Yeah? Here I have a representation of the XOR in terms of disjunction, conjunction, and negation. Yeah? So we have A or B and not A or not B. This is an XOR. And in order to show that it's stronger, we say that this XOR formula implies A or B. Yeah? So whenever the XOR is true, also the disjunction is true. And this disjunction here is the implication, and we want to show that this formula is valid. Okay, when we look at this formula, we could do the formula tree and would identify this disjunction here as topmost symbol. Yeah? This is the topmost symbol, and therefore we apply the rule P or. Okay, now we have to decide which part of the formula goes to the left and which part stays on the right. I put the first part on the left and I get double negation, so not A XOR B, and the A or B stays on the right hand side. Okay, this is what we get by applying the rule P or. Then I eliminate the double negation, we get A or B and not A or not B on the left hand side. Okay, now I have a choice where to continue. I could either continue with this conjunction here. I have only one formula on the left hand side and the topmost symbol is this conjunction here, or I could continue with this disjunction here. I decide to continue with this conjunction here, and the rule for conjunction on the left hand side says just put a comma here and consider the two subformulas independently. Okay, now I could also proceed with the formulas in the antecedents. What I do is I consider here with the disjunction in the goal formula. I put the A on the other side and negate it and keep the B here. Could also do it the other way around. And now what I have to do next is I have here this formula A or B, or I have the formula not A or not B, and in both cases we have an OR as a topmost symbol, and this means we have to do a case split in any case. I decide to continue with this formula A or B, yeah, and then one of these we get a case split, and we have in the one case we have A now in the assumption, and in the other case we have B in the assumption. And if I look at the case where B is in the assumption, then I have an axiom because I have B here and I have B also here in the goal. Yeah, so I have a goal in the assumption, so here I'm done, I have an axiom, and the same holds here on the other side as well. Here I have the other axiom, I have an A here, and I have a not A also here in the assumption, so I have a contradiction in the assumption, which is an axiom. And since I have axioms in both branches of our derivation, I can conclude that this formula here is valid. Yeah? So we do the proof from bottom to top and grow it out upwards. We say, okay, we claim that this formula here is valid, and we prove this by deriving just axioms. Okay, now let's consider another example showing that XOR, or we try to show that XOR is stronger than AND. Obviously this is not the case because we have assignments like this here. A is bottom, B is top, under which the XOR, A XOR B evaluates to true, but A and B does not evaluate to true. Okay, but let's see how things evolve when we do this example. So we have again the XOR here, and as we say now, this A XOR B implies A and B. We again start with this application of the disjunction right rule, so the XOR goes to the other side. We have this double negation here, we eliminate the double negation, we have the conjunction topmost symbol, the conjunction here as a topmost symbol, we do a comma here, and now we have on the right hand side a conjunction as a topmost symbol, so this means we get a case split. We have one branch where we have A as a goal, and we have one branch where we have the B as a goal. Okay, now let's start with this branch here where we have the A as a goal. Then the topmost connective of A or B is this disjunction. We have also to do a case split. In one case, we have now A, then some other assumption, and A also as a goal. So this is an axiom. We are done on this branch. But we also have to consider the other branch where we just have the B in the assumption. And this is not an axiom yet. So we have to, the only thing what we can consider is here this OR, which gives us another case split. In the case we have not B in the assumption, we get an axiom because we have a contradiction in the assumption. But on the other branch, we have B, not A, in the assumption, and A as goal. And now there we have only literals on the left-hand side and on the right-hand side. So no further rule is applicable. Yeah? We could maybe put the A on the other side and put this A there, but this will not help to derive something that looks like an axiom. And this means, okay, we have found a branch where we cannot apply the rules such that we get an axiom. And this means that the formula is not valid because we cannot get this axiom. And this branch gives us not only the information that the formula is not valid, it also gives us a counterexample. Yeah? It says, when we set B to true and A to false, then we have a counterexample to the validity of the original formula. Yeah? And if we set A to false and B to true, then this makes A XOR B true, but A and B false, and this is therefore a counterexample. Yeah? And we can read off the counterexamples by just taking the literals on the right-hand side and negating on the literals on the left-hand side, and by negating the literals on the right-hand side. Yeah? So we would have B, not A, and this would also give us a not A. And this is a counterexample. Yeah? And with this, we can conclude that the formula is not valid as expected. One question is now how we could prove satisfiability of a formula. And this we can do, we now have a tool for validity checking. Yeah? And in order to do satisfiability checking, we can simply negate the formula which we want to check for satisfiability. And if we can prove that the negation of this formula is valid, then we can conclude that the original formula is unsatisfiable. Okay? And if the negation of the formula is not valid, then we get a counterexample why it's not valid, and this is a model of the original formula. And this is the trick to show satisfiability with sequent calculus. And also here for the sequent calculus we have important properties which are soundness and completeness. In this context, soundness means can only valid formulas be shown to be valid, so is the result always correct? And completeness means that deals with the question, is there a proof for every valid formula? And we can show that this sequent calculus, which are also known as Gensen calculus, who was the inventor of this kind of reasoning, that this sequent calculi are sound and complete, which are very important properties of these proof systems. But this will go a bit beyond what we can do in this course. But it's not so complicated to show it. But for us, we assume that sequent calculus is sound and complete. And later in this course, you will see extensions of it for different logics, in particular for first-order logic, and see that we have these basic rules which work for propositional logic, and then we get some additional rules which work for the additional concepts we have in predicate logic. Okay, with this I will conclude the discussion of SAT solving and proving or reasoning with propositional formulas, and I thank you very much for your attention.